Okay, so last lecture we considered the possibility of proposing an alternative privacy notion and then experienced its potential harms. And in a way, for a while, this is what characterized the privacy landscape. Meaning, people were worried about privacy, they wanted to quantify what privacy protection means, they came up with a definition, it seemed quite convincing. Gradually, people found several downsides and several possible attacks, and eventually they realized this definition is not good enough, and then they move on to the next definition. And differential privacy, which we will get to in a couple of weeks, in a way tried to break the vicious cycle and say I have a definition that I can reason about in such a general way that regardless of what would happen after, no general attack will be able to break it. And interestingly, one of the important works that predates differential privacy by a couple of years and in a way led to this definition was a very general attack. So this week we will focus on reconstruction attacks, which are one family of attacks, but what is the result that we will show this week are unique also in the sense of not only the danger that they pose is significant, but also that they are so general that it probably in a way saved us from like several more rounds of, oh, here's another definition, 5 years later we found a problem, etc., etc. It sort of showed the computer science community that it's time to change like attitude. Okay, so this is what we'll focus on today. And we won't be able to move for whatever reason. Okay. Let's see. So I'll just recall some real-world examples that we already saw last week, but just give it another moment to focus. I will show how can we perform reconstruction in an inefficient way, use linear regression-based methods, and then finally linear programming-based methods, which are the way the general result is proven, sort of spoiling some of the mystery, but it's okay. These are things that you should have known from taking the basic course in differential privacy. Okay, so here's the question. We're asking ourselves, in general, the framing where reconstruction attack thinks about is, can we publish data as is? We already know we can't, right? This will lead to privacy danger.
But at what cost?
Yeah, right. We can, of course, exactly. And then we're asking, okay, so does that mean that the only way to protect the privacy of elements in the data set is just to avoid using it at all, providing any useful information? Well, the hope for many years was that this is not the case, and today we know that indeed there are ways to extract some useful information without putting all the users in danger. And one of the important attacks, which is linkage attacks, sort of allows us to simplify and abstract away a lot of the questions. So for a moment, let's focus still on the census setting that we considered last week. There is a matrix, a row corresponds to a user, a person, an element, a column corresponds to a feature, and let's say all elements are public pieces of information, quasi-identifiers, and there's one last row that is binary, again for simplicity, that is private. Linkage attacks is a general name for any attack that uses multiple sources of information to somehow piece together an identity of someone. So the example we saw last week was in the governor of Massachusetts. So what Litania Sweeney did is she said, look, you released this data set that contains only some features, but some of those features are of the users in that data set, which was the health records of the government employees. But some of the data contains, I remember, zip code and age and things like, and sex, I think. Well, those features can be linked to a different data set. In that case, it was voter registration. And effectively what it meant is that every long enough sequence of quasi-identifiers, we should treat it as though it is a deterministic identifier of the user. This is for most users, not for everyone. Some people are very average. There are many people with the same height and same weight and that live in the same area and are hard to identify. But again, we want to provide privacy to everyone. So as long as there's a portion of society that is easily identified by some of these features, it's a problem. So we would consider, when we have a data set with some of the columns as quasi-identifiers, we will consider it as though those columns correspond to just an ID. And now we're asking, can we release aggregate statistics over the last column in a private manner? Okay, so the example we saw last week was this one and this one. I'll go back to this one just so we have a clear visualization. This is also a reconstruction attack, but this is an extreme reconstruction attack. What happens here? Here, a model was trained on, in this example, MNIST. It was trained on a quite small data set, and the release was the model, and the reconstruction was the full images. And as you can see, these are not perfect reconstructions, but are very similar. We want to consider a very general frame of attack. So we don't want to consider a complex output. We want to consider the simplest output, which is just a single bit. And in this case, just releasing 0 or releasing 1 doesn't mean much, because you could guess 50-50 maybe, but if you manage to reconstruct it for a large enough portion of the data, then that is impressive. Okay? So here's the setting we will work with. We have a data set consisting of simply 2 columns. One is an ID of a user, because, as I said, linkage attack, we can think of all the quasi-identifiers as an ID, and one is a secret binary vector. And the only queries that the attacker is allowed to issue are queries of the form, what is the sum of bits in this subset of rows? Now, you might think, oh, this is a somewhat unnatural query, like, why should I agree to answer someone a query of the form, what is the subset of, what is the sum of the secret bits on rows 2, 7, 15, etc. But when you think about it, since this ID corresponds to a whole vector of features, what the attacker can do is issue the query of how many males between the age of blah and blah and this weight and with history of driving drunk or whatever have whatever one in this secret bit. Now this sounds like a very natural question. This is indeed what a typical scientist would do. They would try to find some subset of features that characterizes some phenomenon, and they want to know if something is correlated with something. So this is definitely the type of queries they might do. And since if there are sufficiently many features, they can always express a query which is effectively, I want this subset of rows, in some very general terms. So throughout this lecture, we will just abstract it away and say, well, let's say someone has the ability to construct any query of the form, I want the sum of a subset of indices, and we want to answer with some accuracy. Okay, we're open to the idea of not answering exactly, but answering with some accuracy. And the question is how hard it is for the attacker at this point to reconstruct the original private vector bits with high enough accuracy from these responses. Okay, so let's start with a simple example. Let's say I gave you these answers to these questions. So this is a set of 6 equations over 8 bits. So the variables, the unknown variables are bits, and the answers, I guarantee, are correct up to plus minus 1. So can you reconstruct the private bits from this information?
But each variable can be 0.
0, 1. Everything is binary. Again, for simplicity. Yeah, you might want to use a paper.
We know that in the first equation there is a mistake. It needs to add like 1 to the final results, and in the second and third equation there is a mistake up to minus 1. I'm not talking about still.
Okay, why are you saying that?
Because if we're summing the second and the third equation, it should be like the first one.
Okay, good. So let's make sure everyone follows what Shahar's claim. So equation 2 plus equation 3 are exactly equal to equation 1, right? So we know that if equation 1 says 3, basically the correct answer is not 3, but is in 2, 3, and 4. And here it's in 2, 3, and 4, and the same goes to here. Now, the sum of these two is in the range 4 to 8. Right? And here it's 2 to 4. So, and since the sum of the second and third row are the same as the first row, then indeed we know that now we can say for sure this one is 4, this one is 2, and this one is 2. Okay. So we already know something. What can we do next?
In the fifth equation.
Yes.
It was 3 or 4.
Sorry?
No, the fourth equation was 3 or 4.
The fourth equation. What do you mean about 3 or 4?
The sum is 3 or 4.
Yeah. Okay. Why can't it be?
It can't be 5 because it's summation. But
Exactly. We know the entire vector is 3 or 5. Okay. Good. So now we already have only 2 options here.
we also know that 1 out of x2 and x3 is true, and 1 out of x5 and x7 is true.
Why is
At
that?
least. Well, because we know that we have at least 1 from each side. So, and the thing is, like,
What are the sides? You mean this side, I assume,
Yes.
right? Okay, so let's make it clear. The first 4 have 2 1s and 2 zeros, and the second 4 have 2 1s and 2 zeros, right? That's what we got from the. Okay, so
which also gives us at most 1 out of x2 and x4, and most 1 out of x7, x6, and x8.
right. So if we know that this is 0, which means this is at most 1. So at most 1 of x1 and x4, at most 1 of x5 and x8.
x3 and x7 are yes.
And similarly, okay, so this is a yes already. Maybe let's put it here. This is a yes. Where is it? 5 is a, sorry, not 5, 7 is a yes. Okay. There's another pair of equations that make it even easier to compare.
We know that the last one can't be 3. Or
Right.
can't be
So we have
It
these
can't
2
be two.
lines. They differ by a single element, like one that we subtracted and one that we added. Okay, so the difference could be at most 2, but we have a gap of 3. So we already know if this was truly 0, this one couldn't have become more than 1.
Well, using x3 and x7, we can already say that it's 2.
Yeah.
Exactly 2.
Okay, so we know that this one has to be 1, right? It has to be 1. One of them must have a 1 in them. And that one must be...
We know the last line must be 2.
Right, yeah, sorry. And
X3
then this
x7
one
aren't
has...
there.
Okay,
Yeah.
so we got the 1, we got the 5, so 2 and 4 must be 0.
2 is 1.
Sorry,
2
no,
must be
no.
1. 2 must be 1 because we added it and we got an extra 1. We subtracted
Good point,
that
good point, good point. Okay,
And
So
5.
8 must be 0.
8 must be 0 because we removed it and nothing happened. Sorry,
5 must be 1.
5 must be 1, why?
Since
It's
in
the
the
only one on
third-
the right that can be it.
Yeah.
It's not on the left and therefore must be on the right. And it's the only one on the right that shows up in the last clause.
No, that, I don't see that argument.
Yeah.
Who said maybe this
There are
right
two-
side
there-
doesn't contribute anything?
We calculated from equation 3 that there are 2 on the right side. And we know, we already found the 2 on the left side.
But we know...
We know-
Okay,
So
so
we
it
found
can
the
be
one
one,
on the
okay,
left
right. So it can't be these two, so if this one contributes, then it has to be this one. Now we know that we have one from here and one from here. This works. So now we only need to find who are the 2 here.
We got
So if it's
X7.
not 8, here we have 5 and 7. So here we have an X. Okay? We're good? Alright. So we spent, I don't know, a couple of minutes and we figured it out.
Even by showing up in the middle.
Is this a very practical, scalable method? Not exactly. We need to abstract what's happening here. So, the rest of this lecture effectively will focus on the question, given a set of binary equations that are with solutions that are known to be binary equations over binary how do you put it? Over binary variables, unknown variables. So both the variables we're trying to solve for are binary, and the equations will be only sums. There won't be any weights or anything like that. And we would know that the solutions are correct up to some factor that we will be guaranteed, and we will try to solve it. So this is what we were going to do in this lecture. So, I hope all of you, one second. Good. I hope all of you have the notebook open to follow along. One of the things we'll need to figure out is what is the most efficient way to do it. But I will try to show everything here. It has a lot of explanations if you want to look afterwards. I will basically present everything verbally here. Okay, so. Okay, so the problem setting is we have a matrix. Binary, okay, maybe I already skipped something, but I assume that was relatively clear to all of us. This is a list of equations, therefore it can be represented as a linear set of equations, right? The matrix, the query matrix is a binary matrix. The unknown vector will be of binary values, and the y's, the answers will be, I mean, theoretically they might not be counts, because if it's noisy they might be some arbitrary values, but we know their correct version corresponds to a count, or to an integer. Okay, so that's clear. So what do we do? How do we go about it? So here's a general idea of an attack. Step 1, select the subsets. The queries corresponds to subsets. Step 2, issue the queries. to the entity that provides the responses. And step 3, use those responses to try to guess the correct assignment. Right? This is the general framing from the abstract way. Okay. So, how would we do the subset selection? So, in this lecture, we would mostly consider random subsets. Why is that? So, on one hand, of course, not any sequence of subsets will allow me to reconstruct the entire data set. Give me an example of a setting where the subsets do not allow a reconstruction, even in a case where the queries were correctly answered. Anyone can give an example of a sequence of queries that will not allow reconstruction even when the answers were accurate.
The full thing, well, no. The full thing, half, the other half. Done.
No, insufficient number of queries. That's one example. Who can give me an example of a exponential number of queries and still I won't be able to reconstruct?
Maybe a query that doesn't give anything about the data.
How can it happen?
And query,
Empty query. That's true.
everything else gives something about the data.
Right. But does any new query give me something about the data?
Sums of two queries. Well, no, that. With noise, it can give you something.
With noise, it gives me something, but still, it doesn't give me more than just whatever I knew before. So, how can I get to a point where I'll have exponentially many queries and yet not know something about a big portion of the data? Like what?
Ask lots of queries. Ask all the queries on half the data.
Exactly. It's still the empty query. It's just empty on a half of it. Right? So I can ask, there's 2 to the n over 2 combinations of the second half, and I didn't learn anything about the first half. Right? So clearly, not any set of queries suffices. On the other hand, how many queries will suffice, for sure, if the answers have no error?
How many queries?
So if I tell you I give the responses with no error, what is the maximum number of queries you need to issue, if you chose them correctly, to cover the entire...
I would say n.
Why?
Because every query is basically splitting your answer space. In theory, you might actually need less than n, but every query is splitting your answer space.
Of course, it might be less than n because we just saw it. We had eight random variables and not random variables, 8 variables and 6 equations, and we solved it. So of course
at least log n.
Fair enough, but what is the number that will definitely suffice? This is a set of linear equations. The fact that everything is binary doesn't change the fact that it also adheres to the rules of linear equations. So if I have n rows that were properly chosen, it's good. What is the only condition on these rows in terms of linear equation? That they're independent, exactly. So once you have sufficiently many rows, you know that each one needs to correspond to a new coordinate, so they need not to be, in the case of linear queries that are only binary, it's very simple, just not be the sum of other rows and correspond to new coordinates. So everyone adds a coordinate, that's enough. So the simplest one would be just identity. But that's if I don't add any noise at all. If I do add noise, well, this is becoming a bit more tricky. So now this is basically what we will be exploring. Okay, so in order to simplify things, we will consider random subsets. Why? I'm sort of hand waving it in a high enough dimension random queries or random vectors will be sort of orthogonal. So asymptotically, what we would get from constructing the best m queries attack and what we would get from a random set of m queries will be, let's say, 2m queries, 2m random queries will typically achieve something that is the same as the perfectly constructed m queries. So we'll think of random queries. Okay. Yeah.
Is this basically ignoring the Hadamard matrix, which
Hadamard is a great example for a good candidate for only n queries.
It's proven actually
What is proven?
that I remember from the base course that if you use the Hadamard matrix, you will get up to 16 times the noise square.
So-
on Rome coordinates.
Okay, so I won't get into the details now, but like Hadamard is just one of many queries that of many basically query matrices that are independent. What is unique about Hadamard is that the identity, the correct value should be 1 or 0. So if you add noise that's O of 1, it might mask it and make it useless. But if you issue Hadamard queries, then every row should sum up to about n over 2 if everyone was 1, and then it should be O of that in the general case. So Hadamard is a very good matrix in the sense that it's another way to get a sequence of independent queries, but where the true value is relatively large, so a constant amount of noise it can be negligible relative to the size. But we also have it in the assignment, but more generally it's just like pushing the constants further. The general idea is if you have a random vector which is of size 2n, you'll get something that has effectively the same power as Hadamard, give or take. Okay, so we get so here we have a simple code that just randomly select subsets, and we have some oh, good point. Had I ran it, you would understand what's going on. Sorry, it should have been ran before everything. Oh god, this should have happened. How did I get this one? What happened? Oh god. Sorry. This is going to be somewhat hard to teach when the notebook is not working, and it worked just a moment ago. Okay, that's more like it. Okay, so here's what we see. This is the random matrix, okay, of queries. This is the matrix of queries. Here's the correct responses, and here's some vector of noisy responses. As you see, it's like plus minus 2 from the correct response. Okay. How can we interpret it? So this is one easy to understand visualization. Because the query matrix is binary, I can just draw it in black and white. And because the true value of the vector is also binary, I can also draw it this way. It's a good question. I was like going back and forth between should I draw it as a standing vector or a line down, because for matrix multiplication, this is the size of the data set, the x-axis of the queue, and the y-axis of the queue is the size of the number of the queries. So for matrix multiplication, this should be standing, but then the x-axis were used to be the same one. So I don't know, matter of taste, but as long as you understand what happens here. And you see an example, the orange X's are the correct answers, the blue circles are some noisy answers, and this is what we got. Okay? Here we added uniform plus uniform noise in the range of plus minus 2. Okay, so if the correct answer is 7, we could answer 5 till 9, including. Okay? Similarly, we could also add Laplace noise, which you're familiar from the privacy theory course, but general, any noise, Gaussian noise, whatever. So then we might have some low probability of larger noise, higher probability of smaller noise, whatever. This is the setting. We are guaranteed, the attacker is guaranteed that the mechanism will release a noisy response, which at least typically won't be too large. Okay. And now we want to understand, what does it mean? So we will, in order to have a geometric interpretation, we need to go down to like very low dimension, so you'll have to excuse me. Okay, so let's think about a setting where there's exactly 2 elements in the data set. So this is a binary vector. The data set is a binary vector. A binary vector is a point on the, let's call it hypergrid. Hypergrid, I mean the corners of the hypersphere, of the L1 hypersphere, or the hypercube. Right? So it's one of these 4. Okay, so let's choose a corner. Let's say the correct value is 1, 0. And now I issue a query. So let's say I issued the query 1, 1, meaning give me the sum of all rows. And I know that it will be answered to within some alpha equal, what is it here, 0.3. So that means that this regime is all the answers that might be provided. Why? So the correct answer, if the data set is 0, 1, 1, 0, and I issued the query 1, 1, so the correct answer is 1. The valid answers are 0.7 to 1.3. Okay? This is what these 2 lines correspond to. This is these are all the points. The continuous line corresponds to all the points whose sum is 1. And these 2 dashed lines correspond to all the points whose sum is 0.7 or 1.3. And anything in between is possible. So the mechanism that releases the noisy sum will release some number between 0.7 and 1.3, which will correspond to some line. And then that line will correspond to some subset of possible values of the real data set that could lead to that response. So, in this very low dimensional case, if I know that the answer would not be incorrect by more than plus minus 1, then issuing the query 1, 1 will basically give me a result that will leave me only 2 valid options. The 1, 0 or the 0, 1 data set. Okay, so I'll issue a second query, let's say 1, 0. Now this one corresponds to a row, and that's it. There is only one valid answer within the feasible regime. What is the feasible regime? The feasible regime is all the points that are within. Notice, like, we're doing 2 steps here. Once I define a query, I already define a range of possible responses, and for any of those responses, I know what will be the feasible regime. When I will get an actual response, I will get some number, 2.7, whatever, and I would know that there is some alpha guarantee. So if I got 2.7 and alpha is 0.3, so I know the correct answer is between 4 and 3. And then I would say, well, what are the possible regimes? Okay, so basically I know that with 2 queries, I will limit the feasible regime to a subset that is that can contain only a single element. Okay? And we can still see it in 3 dimensions, though I can't say if this is worth the headache, but okay, here it's 3 dimensions. Okay, so now it's a cube. Okay, and again, let's issue some query. So here, this is x1, is this side, x2, and the height is x3. So, I don't know, choose some query.
111.
Okay, so 111, what would it do? So let's think about it. The correct answer should be 2, right? So 111 will provide an answer, I don't know, here it's now between 1.8 and 2.2. So it will create sort of a diagonal weird slice. Okay, so let's rotate it and then we can see it. Okay, now we can see it. This is a hyperplane plus width, like a slab, that crosses the 3 points that their sum is 2. Right? So this one, its sum is 3, and these, their sum is 1, and this one, its sum is 0. So these 3 points are candidates. Okay, again, now, had the slab been wide enough, it might have also included these ones. You see, now the slab is so large that it only excludes the 0, 0, 0. But for narrower slabs, it already gets rid of all but 3. And then you add another one. We need to turn it now and some. No, I think this one. Okay, this one just excluded one option. These are really hard ones to visualize. But, maybe it's going to be easier to have this type of queries. I think these are like a bit easier to, right? Each one is sort of a hyperplane, and I'll make it a bit narrower, so it's going to be easier to distinguish. So you see, this one is sort of this one is like this diagonal, this one is like this diagonal, etc. Okay, each one is like a diagonal in high dimension. Okay, but what is important here is not like the actual visualization, but like the idea of what happens. So we have a point on the grid, and we have a query that is that has a correct answer. So it's a hyperplane, and then there is inaccuracy, which make it wider, and then everything that is within that range is a possible answer. And then we'll have a bunch of them, and as long as we have enough, we can truncate it to have like just only a single grid point within that regime, and we can solve it. So how will we solve it? So the first natural option is brute force. We did not do brute force in class 10 minutes ago, but we could have. It was just 8 points, right? 2 to the 8 is not that terrible. You consider all of them, all of the assignments. Now, if you're guaranteed that it is within plus minus some alpha, so you can either run over all the assignments and just find one that is valid. That's one option. Or alternatively, you can say, I will choose the assignment that minimizes the worst error. What is the worst error? That's L infinity of the errors, basically. Right? Every assignment and sequence of queries has an error. Think about the situation from the attacker's perspective. From the attacker's perspective, the orange x's are unknown, and the circles is what is known. And the attacker tries to guess the assignment to this vector. So when we put an assignment, we get the x's, and the errors from the attacker's perspective are not the distance of the circle from the x, but the other way around, the distance of the x from the circle. Right? When we know how the answers were generated, we start from the x's, they correspond to the correct answer, and we then generated a response that is a noisy response. The circle may deviate from the x. From the attacker's perspective, it's the other way around. They know the attacker observes the circles and it tries to guess what are the x's. So any assignment gives a vector of x's, and any assignment has some vector of errors, the size of the queries. So let's say you choose the one that minimizes the number of the worst error, the L infinity. Now, this is somewhat arbitrary. Like, as long as I require that all of the responses are within the correct range of alpha, any vector is legit. I can say minimize L1 under the restriction that all of the errors are under alpha for some fixed alpha node. But simplest way is just minimize it. So let's just visually see what it looks like. So here's what we do. So this is an example of, what is it, like n equal 12, m equal 22, just random numbers, and alpha equal 1.75. Okay, notice this is not a very small alpha because n equal 12 and everything is random, so it's about half. So the correct answer should be about 6. So alpha equal 1.75 is not negligible. And how should we interpret it? So now every point here on the graph is as a possible assignment. So this is just 2 by 12 assignments, not that many, so I can plot all of them. The x-axis is, and this is for a specific vector of responses that was produced from a specific data set. So there is some assignment of binary values to the n values, there is some assignment of binary values to the m by n matrix, and there is some response that was produced. And then on the x-axis, we plot all of the L infinities that each of the different queries, each of the different assignments get. And on the y-axis, we plot the Hamming distance between the assignment and the correct solution, which is effectively the number of incorrect bits. And not very surprisingly, the ones that are below alpha have all relatively low Hamming distance, and the correct answer has the lowest one. And this points out to a very important property. When we think of optimizing something under some constraint, one of the first questions we should ask ourselves is there even a solution? Not necessarily every optimization, any constraint optimization problem has a solution. But why are we guaranteed that we will have a solution in this case?
Because you have the data.
Because the correct data, we are guaranteed that the responses are within alpha from the correct values, so the correct assignment is definitely within the feasible regime. So we're guaranteed that there's going to be one element there, and we're guaranteed that the rest will not be way too far. So we will get to the formal claim later, but the intuitive version says that if we are guaranteed that all responses are correct within plus minus alpha, and we have an assignment that is alpha accurate, then alpha accurate, I mean the responses it induces are within plus minus alpha, then its Hamming distance must be at most, if I remember correctly, 4 alpha. That is one of the intermediate steps in the Dino Nissim paper that I mentioned before. That was the one that showed the general powerful attack, a reconstruction attack, that in a way led people to understand we need a very general privacy notion. Now, this result in itself is not very impressive because all it says is that if the attacker has exponential time, then it can reconstruct the data. But if the attacker has exponential time, it can break any encryption probably, so that's not very frightening. So if this was all we could say, no one would be excited about this result. But at least it tells us that from the information theoretic perspective, we know how much knowledge is leaking when we give these responses. Okay, let's take a break.